Our today's colloquium speaker is Ryan French. Ryan is a PhD student at the UCL Mullard Space Science Laboratory. He just submitted his thesis last week. He's also a NCAR fellow here at NCAR High Altitude Observatory, where he has just returned to the UK from a 4-month visit in Boulder. In his PhD research, Ryan uses spectroscopic and spectropolarimetric observations from ground and space-based telescopes to probe the dynamics of explosive energy release of solar flares. Ryan is also an enthusiastic science communicator with experience teaching astronomy to the general public at museums and historic observatories. Today, Ryan will be talking on probing current sheet instabilities from flare ribbon dynamics. To Ryan now.
Great, thank you so much for the introduction. Yeah, we were just chatting before most of you joined that when I wrote that bio, I hadn't yet submitted my PhD thesis, so I was optimistically committing to have submitted it by the time I did this talk, which thankfully I did do. So submitted my PhD thesis on Friday just gone, so still riding the wave from that a little bit. And the work I'll be presenting today is actually from the third paper from my PhD research, probing current sheet instabilities from flare ribbon dynamics. And I will be talking, I'll advertise this now, next week at the NSO seminar, not talking about PhD work, talking about work from my recent visit to HAO. So 2 talks, different topics, different weeks, but today we're talking about solar flares. Okay, so let's get started then. So the standard model of eruptive flares. I'm sure a lot of you are familiar with this. On the left, we have a very simple 2D cartoon. This cartoon often criticized for being overly simplistic, but I quite like it. I think it's fairly good at summarizing a lot of the observables that we see in solar flares. So in the standard eruptive model, you have some sort of higher altitude magnetic structure, such as a flux rope with an overlying magnetic field. And if under this magnetic structure, there's an inflow of these magnetic field lines, you have a situation where you have oppositely orientated magnetic fields and your magnetic reconnection can occur. The region where reconnection occurs is called the current sheet. And in 2 dimensions, you can't really see what's going on. The current sheet is shown as an X point, which isn't really what happens in reality. In 3D, the reconnection occurs along a sheet known as the current sheet. And this image on the right, this is another cartoon of the same standard eruptive flare model, now in 3 dimensions, and you can see the horizontal extent of this current sheet region. And from the reconnection site, we have the outflow of higher energy particles, high energy plasma, and as these flow down the magnetic field lines and they intersect with the chromosphere, you have a situation where you have the less dense, higher energy material colliding with the lower energy chromosphere, and you get chromospheric evaporation or sublimation of material down here in the chromosphere, causing it to glow. And these are visible very bright in UV and EUV, and we call these flare ribbons. And again, 2 dimensions, not doing it much justice here, but in 3D, you can see the full extent of the ribbons, and you can really see how this ribbon is directly connected to this current sheet region. And as the region of your reconnection evolves, or as these field lines shift, the connection or intersection between those field lines and the chromosphere too will evolve in space and time. So the ribbons are not fixed structures. But one thing that the standard model of flares doesn't address is the nature of reconnection itself. So reconnection was sort of first introduced back in 1957 by Sweet and Parker. And the initial configuration was that reconnection would occur along oppositely orientated field lines, and it would occur along the entire length of those field lines. So the current sheet would be your full length of your field lines here. And although this can sort of account for the changing magnetic topology that we observe in flares, the energy release rate through Sweet-Parker reconnection is far lower than what is actually observed in solar flares. So this then led to further developments. PET-check reconnection was a big jump in 1964. And in PET-check reconnection, your reconnection only occurs along a small fraction of the sheet. And this model was a big deal because it was able to account for the observed release or rate of energy release that we see in flares, but it was unclear that the configuration like this, which must be sustained by slow shocks, was unclear whether this configuration can be sustained in flares or if it is sustained in all flares, if it is sustained in some flares, for example. So in recent decades, attention had then instead turned to plasma instabilities. And one key example is the tearing mode or plasmoid instability. And what happens in this case is that if you have a current sheet whose length greatly exceeds its width, if that ratio is large enough, then the current sheet will collapse at multiple points along the sheet. So instead of just one X point where reconnection is occurring, you have reconnection at multiple sites, which you can sort of see from this very simple cartoon here, forms these magnetic island structures. And then if you imagine if I zoomed in further again to this magnetic island here in the middle, I would again have a similar sweet Parker current sheet, which again can collapse into even smaller magnetic islands. And these plasmoids or magnetic islands can continually break down in this way to progressively smaller and smaller scales until you create something which looks like a turbulent cascade, or similar to a turbulent cascade that we observe in situ measurements of turbulent plasmas, for example. So that meaning you have a power law of different sizes of these magnetic structures. And not only can these magnetic islands break down to be smaller and smaller, you can also have reconnection sort of at other boundaries as well. So you can have the coalescence of islands. So you have islands growing as well as shrinking and breaking down. So my PhD research really has been investigating the role of the tearing mode instability in solar flares. So my first two chapters of my thesis look at an example from the September 10th, 2017 flare, which is a very famous event. It's the second largest flare of the previous solar cycle. And the reason it's so famous and so well studied is, one, it occurred right on the edge of the limb. So you get this sort of edge-on profile view, and the alignment of this thing means that it looks very similar to the two-dimensional model of flares, which we looked at earlier. But also, because it was the only active region on disk at the time, everything was looking at this flare, and it was captured in a very large range of observations, including the HAO comp instrument. So I won't be talking about this today, but in my first two papers, I look at comp data of the solar flare, looking at evidence of the tearing mode instability in this event. But as I said, this event was one of a kind, a very rare observation data set. So really, we can't rely on these very rare cases where the flare is at the limb and you can actually see sort of heated plasma around your current sheet. Those data sets are very, very rare indeed. But instead, what we can utilize, instead of waiting for a flare to erupt on the limb where we can see the current sheet region, instead we can turn to flare ribbons. Okay, so due to the connectivity between the flare ribbons, which we see on disk in the chromosphere, due to the connectivity between these and the higher altitude current sheet, the reconnection site, which we can't always see if we're looking face down on the sun, because of their connectivity, behavior of the ribbons must reflect processes up in the current sheet region. And there's a few good papers that have looked at this sort of thing and have found spectroscopic signatures in the ribbons that are suggestive of waves and or turbulence. And this is consistent with the idea of the presence of the tearing mode or the Kelvin-Helmholtz instability up in the current sheet. And you're seeing the remnant of that as it's flowed down your field lines and it's reaching the chromosphere down here. But in this study, we don't turn immediately to spectroscopic observations. Instead, we actually take motivation from a study of the magnetosphere. So I didn't know a lot about this until I started this project, but flare ribbons, which we see in the sun, are very analogous to auroral beads here in the magnetosphere. And this is a term that I wasn't too familiar with. But similarly, as in the sun, you have your reconnection site, your X point, and your high-energy particles flow down the field lines and intersect with the chromosphere. On the Earth, above us, we can have on the night side of the Earth reconnection, and then similarly to on the sun, the high-energy particles come down and intersect, and that's how we get the aurora, of course. But what I hadn't realized is that the aurora can show magnetic substructure as detailed and intricate as what we see in flare ribbons. These are called auroral beads, and this is a new term for me. And just comparing on the left, this is some SOT observations of flare ribbons, and here on the right, some auroral bead observations here. And they sound nice as well, don't they? Flare ribbons, auroral beads, sounds quite nice. So this work was actually motivated by a study of these auroral beads by Nadine Calmoni et al. She was a PhD student and a postdoc at UCL, where I've been doing my PhD. And what they do is they look at the intensity variation across these flare ribbons, and they calculate the fast Fourier transform, the auroral beads. They calculate the fast Fourier transform along this auroral arc to search for key spatial scales occurring. So you can sort of see by looking at this, say 1 bead, 2 beads, 3 beads. So they look at spatial scales along this structure. And they compare the growth rate of these scales and the duration of these scales with the growth rates and scales predicted by the theory for different reconnection instabilities. They were looking to search for what instabilities are occurring out in the magnetotail, the projection of which they're observing in the auroral beads. And I think they find most compatible with an obscure instability that isn't relevant to solar physics, the shear ballooning instability, I believe. But anyway, we take motivation from this study. And so our aim then is to search for the growth and timings of key spatial scales along the flare ribbons, just as was done in the auroral beads, for a small, simple event. And so what does this look like sort of from a cartoon perspective? If you imagine your classic sort of flare scenario here, you've got your flare ribbons, which are then connected up to the current sheet. And so if you have processes or structures within this current sheet region here, whether it be waves, evidence of turbulence, unlikely to resolve specific islands, but the projection of these, or I guess a cut along the current sheet here, I should say, we're then seeing or looking for the projection of that down here in the ribbons. And then we aim to compare these parameters with those predicted by the theory of different instabilities in solar flares, and as well to the timing of flare onsets and plasma turbulence. So the flare we look at is a very, very small event, almost insignificant. You wouldn't probably even notice if you're looking at a full disk image. It's a B 1.6 class flare, I think. So a B flare, barely anything. And you can see it's happening in the very core of this active region here. But the flare was observed by IRIS. It was observed with a sit and stare routine, just the one slit jaw imager filter, the 1400 angstrom line. And so it was able to capture this flare with a very high cadence of 1.7 seconds. So we have imaging in the slit jaw imager. This is a cropped version here, but we also have Spectra, the sit and stare slit, which you can see the position of this slight intensity enhancement here. So the slit, where we have Spectra, is actually crossing this ribbon here. And you can see we have two ribbons. On the bottom left, this is the sort of the light curve of these two ribbons here. You can see they brighten cotemporally, and following the sort of peak brightness, we then have the appearance of these flare loops in AIA as well. But furthermore, beyond just looking at the intensity of the ribbons, if we sort of track the area traced by these ribbons as they sort of move and evolve, the photospheric flux, so from HMI line of sight magnetic field measurements, the photospheric flux traced by these ribbons is consistent throughout the evolution as well, or at least through the rise of the flare. So what this tells us, the fact that flux is being matched in these two ribbons, we can almost imagine a tube of flux from the one ribbon to the other, and the field lines within these ribbons are reconnecting between themselves. There must be reconnection. We see the flare ribbon enhancement here, but they're not reconnecting to any external fields. So because this is a very small and simple event, we can almost think of this as a closed system, these field lines reconnecting with nothing external to the lines between the ribbons themselves. And we definitely wouldn't have that scenario for a much larger event, as they're a lot more complex. So we deduce this is most likely an example of quadrupolar reconnection, but the flare is so small that the sort of the quadrupoles sort of blend into a single ribbon on each side. But as we discussed in the paper, the work from this study, it doesn't really matter what the configuration of the flare is, because even if you have a circular spine flare or something like that, where you would have a magnetic null rather than, say, a current sheet, you still get these instabilities, like the tearing mode instability in those areas. So we say most likely quadrupolar reconnection, but in essence, the results and conclusions, independent of whatever you might deduce this flare to be exactly. Now, this flare, the spectral data from IRIS was looked at in quite a lot of detail from this paper from Natasha Jeffrey et al. And so they're looking at just the spectral observations, which, if you remember, was looking at the left ribbon, the east ribbon, which was the largest of the two. And what they find the non-thermal velocities, that's excess broadening in the emission line beyond the thermal width. They find that the rise in non-thermal velocities, this blue curve here, precede the rise in intensity, which suggests that the plasma turbulence is occurring or observed before the plasma heating and the corresponding flare onset. And they also note that the ongoing presence of this turbulence signature, which lasts for quite a while, the ongoing presence of this means that the driver of this turbulence must be persisting for longer. They don't really deduce what could be causing this turbulence that we see. And so what we do then is we leave the spectra behind for a little bit, and we turn back to our original aim of tracking the intensity variations along these flare ribbons. And so what we do is we write a little routine which tracks sort of a centroid or a central slit that follows the sort of the center of gravity, if you will, of this ribbon as it evolves in space and time. And we then take sort of a average of 3 pixels, 3 by 3 pixels around each point along the centroid, just so we're not looking at the precise middle pixel, but we've got some coverage there, and we plot the intensity along these ribbons. And next, what we do is we process this signal and we calculate the fast Fourier transform, and we do this for every single time step, so once every 1.7 seconds. And then what we get from that are these two plots here. So on the left, this is a stack plot of intensity. So along the bottom is time. So every vertical slice here is just this intensity cross-section that we showed before. And on the right, each vertical cross-section here is the output of the fast Fourier transform, so the power. So what this is showing is the spatial scale, so different scales that are occurring along this ribbon. The power of those scales is the color, and as that evolves in time. And what we see is we see the growth of, well, across all wavelengths really, up to 6 orders of magnitude in power. And crucially, beyond us seeing growth across all spatial scales, we see that the start time of this growth, if you look sort of in this region here, the start time of this growth appears to vary with spatial scale. And I've got to be careful here. So I say wavelength because technically talking about wavelength then not wavelength like spectra, but wavelength is in the inverse of wave number, which is what we're looking at here. So spatial scale, wavelength. I'll try to say spatial scale to avoid confusion there. Okay, so this is just for the east ribbon, okay? So this is the largest of the 2 ribbon, but we can do this for both. However, if we want to be sure that the spatial scales we're seeing in each ribbon are a process or are related to processes up in the current sheet itself and not related to, I don't know, scales intrinsic to the chromosphere itself, what we can do is use this idea of conservation of flux. If you remember at the start, I showed you that we have conservation of flux from one ribbon to the next. And so if we have spatial scales occurring up connected to both of these ribbons, such as at the reconnection site, for example, these spatial scales, as they travel down the flux tubes and the field lines to either ribbons, those scales will scale themselves depending on the size of those ribbons, if that makes sense. And I've tried to demonstrate that with an example of a wave and these magnetic island structures. If these were imprinted perfectly into the chromosphere, you'd see them at a different size depending on the ribbon size and how close together those field lines were. And so what we can do is we can take the spatial scales that we see in the east ribbon and spatial scales we see in the west ribbon, and we can sort of convert the scales from the west ribbon by the square root of the ribbon areas to put the scales from the west ribbon into sort of the reference frame or the sizing frame of those in the east ribbon, if that makes sense. And that is indeed what we do, and that will be crucial in just a moment, as I will show you. And then what we do for both ribbons is we take our power spectra, we take a horizontal cross section along the power spectra. So now we're looking at the growth in power at a given spatial scale as that evolves in time, which looks something like this plot on the right here. And we see exponential growth. This is a log on the y-axis here. So we see exponential growth. And to examine how this exponential growth is changing with wavelength, we fit sort of a region of exponential growth here to determine the growth rate and the start and end times of the exponential growth. And we do that at every single wavelength. And this is what we find. So there's quite a lot happening in these two curves. This curve on the left is showing the the exponential growth at different spatial scales. So we have the growth rate on the y-axis and the spatial scale on the x-axis. And on the right here, we're showing the spatial scale again, but we now have the start time, these bottom curves, and the end time of this growth. And for the east ribbon, the brightest ribbon, that's in the cyan curve. And for the smaller ribbon, the west run one, so we have less pixels, so it's a bit more noisy, but that's shown in the red curve here. And we see a nice sort of matchup between the peaks and the troughs. A bit noisier in the growth rate, but certainly when you're looking at the start and end time or the start time, we see there is a matchup of when these different spatial scales start to grow in each ribbon. So remember, if these scales are related to something intrinsic to the chromosphere or the photosphere, granule size or something like that, then you would expect the sizing of these scales to be the same in each ribbon before you do any scaling. But after we scale via the area, that is then when we see this nice matchup with this trough here in particular. So this convinces us really that these processes causing these spatial scales in each ribbon are connected to that common point of connection up in the reconnection site. And looking at this plot on the right here, this bottom half as well is particularly crucial. What we're seeing is spatial scales of around 1.75 megameters. This is just the projection of these scales onto the chromosphere, so not actually the physical scales up in the reconnection site. But we see one key scale start to grow first, which is then preceded in time by the subsequent growth of progressively smaller and larger spatial scales. So this is evidence of, well, it appears exactly like a cascade to smaller spatial scales and an inverse cascade to greater spatial scales, starting off with this one critical point. And so the observables we have from these plots then. So we have exponential growth occurring across all wavelengths, okay? And we see that occurring with this preferential scale. And this growth across all wavelengths is expected from plasma instabilities in general, not just the tearing mode, for example. But the fact we see this preferred spatial scale, we see exponential growth rates of 0.1 to 0.2 per second. And we also see this evidence of the simultaneous cascade and inverse cascade. The only really serious candidate of instabilities in the plasma sheet that can fit these conditions is the tearing mode instability. So we believe that this is evidence of the tearing mode instability manifesting itself up in the current sheet, and we're seeing the remnants of the projection of that down at the flare ribbons. And so what we can do then is we can take the spatial scales which we observe, and so this blue curve and this magenta curve, this is the start and end time of the east ribbon growth. It's the same plot as before, but now flipped. Time is now on the x-axis. We can compare this with the non-thermal velocities. So these were the non-thermal velocities that were studied by Jeffrey et al. That we have the spectra for crossing the east ribbon. That's why we do the comparison between just the east here. And what we see is that the exponential growth, which starts at this key spatial scale here, this exponential growth is preceding the initial rise in non-thermal velocity by about 15 seconds. And similarly, when our exponential growth ends, it's about 15 seconds before these non-thermal velocities decay back to background level. And so this is indicating, or at least consistent with the idea, that the plasma turbulence here, which is related to the non-thermal velocities that we observe, it's indicating that the plasma turbulence is almost being driven by the tearing mode instability for this confined flare. Okay, so that's sort of one of the key results here, the tearing mode instability triggering this plasma turbulence. And to sort of back this up and gain a bit more confidence that this is actually what we're seeing, we can turn once more back to the initial power spectra. And if you remember when I introduced the tearing mode instability at the start, I said how we expect a turbulent cascade. So you have to break down to smaller scales, but also the coalescence to larger scales. That's how we get that cascade and inverse cascade. But these eventually reach a power law, which is a classical sign of turbulence. Now, different simulations of turbulence yield different power laws, okay, in the spatial domain. And that will depend on the initial conditions, what's happening, et cetera, et cetera. But when we started looking through the literature, we got pretty happy, because if we then take, again, a vertical cross-section, so this is just looking at the initial power plot at a given time, plot this in log space, we get this plot here on the right. So these different colors show different times. And what we're seeing is down here at earlier times, there's not much of a power law here, not a lot of, well, it's not linear on log, which you would expect for a power law. But at 1037, which occurs at the peak of exponential growth, so these colors along the bottom here correspond to the colors here on the right, at the peak of exponential growth, we finally reach a power law of 2.3. And when you look in the literature, when you look at simulations of tearing mode induced turbulence, they find a power law of between 2.2 and 2.5. So the power law that we're finding here in the observations is consistent with that of tearing mode induced turbulence in simulation work. And if we combine these sort of two plots together, they're basically just different ways of showing the same thing. Back here, before we see any exponential growth, we see there's nothing. So this yellow line here, not really much signaling the power law. If we then move on to green, so at this point, everything has started to grow. As you can see here, everything is growing, sort of being led almost by this key spatial scale, which is the first one to start growing. And then by the time you reach the peak, you've got this power law, which then starts to decay again, following the decay of the non-thermal velocities, decay of the turbulences we see. So to conclude what we discussed today, the behavior of the spatial scales in the flare ribbons, which we observe by looking at the fast Fourier transforms, the behavior of those are consistent with the presence of the tearing mode instability in this flare and current sheet. And the relative timing suggests that the tearing mode instability is triggering this plasma turbulence through a cascade, an inverse cascade, reaching this end power law of 2.3. And if you remember back to the Jeffrey et al. Paper, which I discussed, they find that the non-thermal velocity rise that we are proceeding with our spatial scale growth itself is preceding onset of the flare. So this is all happening in the pre-flare, if you will. And this is starting to shed light on the interplay between reconnection, turbulence, current sheet disruption, etc. This is, of course, just one flare. My plan would be to expand this to a number of flares. This was a confined event. It would be nice to compare with eruptive structures of different sizes and to see if there really is a pattern here in terms of the power law that we see these structures starting to grow at, or if this is just if we did just get lucky with this one time. Of course, we need to look in more examples. So that is the end of my talk. I went through that fairly quickly, but lots of time for discussions and questions. And I just want to advertise again, next week I will be presenting at NSO, some recent work with Roberto, Phil, and Tom, who are on this call. So thank you very much for listening, and I welcome any questions.
So thank you, Ryan, for a very nice talk. Now this is open for question, and either you can jump in and ask your question, or you can write in the chat, or raise your hand, whatever works. Phil.
Thanks, Ryan. I had just had a very simple question. At the beginning, you talked about the magnetospheric effects on the ionospheric aurorae, and are those pictures purely of plasma emission, or is there a magnetic component to the auroral measurements that could also be looked at in terms of the plasmoid kind of structure that you're advocating?
Yeah, so I'm sure there are probably people on this call who know more about magnetospheric instrumentation than myself. To my knowledge, this is just intensity measurements. So this is just related to the deposition. So there's no sort of direct magnetic field measurements here, but these are almost being interpreted similarly to the way that ribbons evolve as the point of intersection between the field lines and the ionosphere, but no direct field measurements, no.
Okay, so it's basically, I just wanted to understand what it's showing, and you think it's showing us like energetic particles, electrons, that have originated in structures which are smaller, far smaller than the actual large-scale structure. But furthermore, they do apparently have this scale associated with them. I mean, the two left panels show rather consistently one length scale, which I think is what you've argued on the sun as well. Is that right?
Yeah, that's sort of what we're going for. Obviously, and again, maybe someone will tell me that I'm wrong here, but to my knowledge, there's a lot less happening in terms of changes in temperature density between here and here compared to between here and here. So here we get these nice, clear, sort of bead-like structures, whereas in the sun, we're never going to see something this discrete as we see here in the aurora.
Okay, thanks.
Yuta?
Hi, can you hear me?
Yep.
Yeah, thank you for the interesting talk.
Thank you.
I have a, maybe I missed the explanation, but I have a question about estimation of non-thermal velocity. Can you go to the slide?
Yes.
The page. So,
right here.
So yeah. How did you estimate the velocity from the line profile? Do you have any assumptions, or what kind of fitting or something like that? Can you explain?
Yes. So the silicon 4 line, which we're observing here, is optically thin. So it's an emission line. So essentially, yeah, I think I definitely skipped over some steps here. So you have the width of your emission line, and in general, unless you have some extreme processes, emission lines can be fitted quite nicely by a Gaussian profile. And if you have your Gaussian profile, you can take the full width half maximum of that. You can subtract the broadening that you get from the instrumental broadening, that's quite known. And then you subtract the thermal broadening. There's a bit more of an assumption in subtracting the thermal broadening, because you have to assume what the temperature is. So the standard for that is you take the temperature be sort of the peak formation temperature of that spectral line, so silicon 4 in this case. So you subtract that width, and then the width that you have left, we call your non-thermal width. So this is width in the emission line that's not being caused by the instrument. It's not being caused by the sort of temperature of the plasma. So there's something happening in the line of sight it's not a bulk plasma shift, so it's not Doppler shifting the line. You have processes sort of with no preferred direction, right? So we call that the non-thermal width, and then from that width, you would just convert that to a velocity, similar as you would convert sort of a regular Doppler shift to a velocity.
How,
To get the non-thermal velocity.
then how do you estimate the temperature? Because thermal estimation of thermal velocity can affect on estimation of non-thermal velocity, right?
Yeah, so you would take it as the peak temperature at which this line forms at. So if you imagine for a given spectral line, so this silicon 4 line, for instance, so that is, I forget the exact specific wavelength that's within this band, that's the main contribution here, has a contribution function. So it has a peak intensity at a specific wavelength and, sorry, a specific temperature and density. So it's fair to assume that the bulk of the emission here is within or coming from a relatively narrow temperature, causing that peak intensity. But as you can see from here, there's quite a large change in the full width. Well, here we show it as, or it's shown as the full width half maximum, but there's a fairly significant change here, and then yeah, you can convert this to non-thermal velocity. So in essence, yeah, there is an assumption with temperature when you do convert this from just the full width half maximum to the non-thermal velocity, but the two curves, if you plot them side by side, don't change that much.
Okay. Thank you very much.
Yeah, thank you.
William?
Hi, Ryan. Great talk. Awesome.
Hey, thank you.
I just had a quick question about the spatial scale that you measured. So there's a critical spatial scale, like you said, 15 seconds or so before you see the, yes, right there, perfect. So yeah, the spatial scale is about, 2 megameters or so. And this is measured from silicon 4, right? So this is in the chromosphere transition region. I'm not super familiar with some of this other work where we expect the spatial scale to be correlated to this Terry mode instability, but is the spatial scale around 2 megameters or so? Does that correlate to a similar spatial scale in the corona?
So I guess I'll show this very simplified cartoon here. So if we had more observations of this event, right? If you knew perfectly, if you had magnetic field measurements of the corona, or if you had even, because we're not perfectly on center disk, if on center disk if you're on center disk and had extrapolations, for instance, if you had a better idea of how these scales projected onto the chromosphere, or how the flux tube, I should say, grows and shrinks in the corona, then you could back map and say what these scales are actually at the reconnection site. We don't have enough observations in this instance to do that. We're only talking about the projection of these scales here onto the chromosphere. But in theory, if you had enough measurements, or if you were confident at, well, you wouldn't even need to know the size of this region or the width of this region, because we are scaling by magnetic flux, right? So if you had a magnetic field measurement up there in the where you suspect the reconnection site to be, you could give an estimate on what these sizes are, but we don't have the observations, at least for this flare, to do that.
Gotcha. Cool. Thank you.
Thank you.
Sarah?
Really nice talk, Ryan. Thank you. I was wondering, I've seen some simulations with Turing mode, large scale global type simulations with Turing mode, and I'm wondering if you've looked at those or thought about those, or if they'd give you any intuition, and including the kind of thing you're talking about right now for how you might diagnose that and the kind of observations.
Yeah, so how would I, so I guess as this work, or if I progress this work further, it would be required, as you did a statistical study, more events to lean more into those simulations, and maybe even to do this exact analysis for ribbons of these global flare simulations and see if it pulls out what we think we're seeing here. So we certainly, I think the simulations that we take a look at here are not all flare specific, more general Turing mode reconnection models. So doing those comparisons with flare simulations would definitely be a next step. Yeah.
Yeah, and I was also thinking, you were just talking about if you could get those measurements of the magnetic field, you know, like what would that take the form of? What kind of measurements would work? Would you need like measurements of circular polarization from, I mean, what would you actually use? Or could you use linear polarization topological measurements like you've done in the comp before, or?
So let's think. So there are different ways you could do it, and there are definitely pros and cons for each. Perfect case, which, let's be honest, is almost impossible this is going to happen. If you had Solar Orbiter and DKIST at perfect quadrature, and you had EUI looking down with high cadence of these ribbon structures, and then on the limb you had sort of Ionosphere imagery with Stokes V, then that would give you the full picture, right? But that's probably not going to happen. So what you could rely on instead, maybe you had a magnetic field estimate from radio observations, for instance, or there have been some studies recently with Hanode ice to get magnetic field estimates out from the corona via that, or even if you had a flare near center disk and you were able to do some nonlinear force-free extrapolations, and if within those extrapolations you found like a QSL layer or a null point or something like that, then you could even use those extrapolations to get an estimate for the magnetic field there. So there are options depending on what data is available, and obviously pros and cons and different likelihoods of those data sets happening. But I think it is possible. Yeah.
Yeah, and I mean, depending on the spatial scale, and this is actually something I'd be interested in getting a better sense of. If we have an L5 Doppler magnetogram at L5, which probably will happen at some point, and we get Cosmo, where you're actually observing the full global corona, because the issue with Ionosphere, of course, is you just have to be actually looking at the right place at the right time. Whereas if you have a synoptic global type thing like Cosmo, you could do it. So then the question would be, what sort of spatial resolution would you need? And then the question is whether Cosmo could do that. Do you have a sense of that?
So the argument that we're going for here is we're not saying specifically that we'd be able to resolve these individual structures, but more that if you knew what the magnetic field was here, you could almost back map the size of these things to the size of the corona, sort of just by comparing the magnetic field strengths, conservation of flux. And then depending on what that scale is, you could say, okay, we would expect to see it or we wouldn't expect to see it. But I don't think it's necessary to see it. And then your question perfectly relates to some of my previous work with comp, which actually shows that you don't have to perfectly resolve these features and able to learn something from them. And this magnetic substructure that you might get from these magnetic island features can be seen in linear polarization, even if they are happening on sub-pixel scales. So I think definitely Cosmo, if we get that, would be a great help for all of my research, really. So
cool. Great, thank you. Nice.
Thank you.
Any other question? I don't see any hand raised. If you have any question, just speak up. Okay, so I don't see any hand raised. So let's thank our speaker again for a very nice talk. And I think some of us will be attending your NSO talk again.
Great. I look forward to seeing some of you next week then.
And congratulations again.
Yep, thanks.
Thank you. Yeah, thank you for having me. Bye-bye.
Bye-bye.